Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 3 of rectifiers chapter, right? So up until now we have studied half of a rectifier with pure resistive load and with battery, that is RE load. Now we'll study a bit about filters and we'll study a bit about inductors and capacitors. We'll just revise the thing that we know about inductors and maybe you may learn something new today also with inductors and capacitors which you don't know, which you didn't knew beforehand. So that's why I had taken this inside and this is not kept in the prerequisites. So maybe you will learn some new information here. Okay, so also we'll do few questions, right? And also we'll cover half-wave rectifiers with pure inductive load. I have covered this already with diode, but with simple SCR, right? I haven't covered it, so I will cover it. So let's start with filters. So what are filters basically? Filters are required basically to control the ripples. I have told you, right? Whenever there is a rectifier, basically the output load that we get is not pure DC, there are ripples in it. So to remove those ripples, we need filters. Filters filter out the ripples, as the name suggests. In control uncontrolled converters, output voltage VO and IO contain high ripple components. Filters are used to control these ripples in VO and IO, that is output current and voltage. While power electronic devices can be used to reduce ripples, they are not economical for effective ripple control. That's why we use LNC. Okay, we will see what are the use case. I have already explained this capacitive filter in my prerequisite. I will explain about this inductive filter here. Okay, so low pass filters are generally employed to control the voltage and IO ripples, ensuring smoother output. Inductors are used to control the ripple of current and capacitors are used to control the ripple of voltage. So whenever you associate capacitor, right, you associate it with a voltage, and for inductors you associate it with currents. Okay, so these two things you do. Now there is a quick recap of inductors. Let's do a quick recap, right? We know everything. I'll just do a quick revision. So if current is entering into this inductor like this and voltage is measured, like voltage will develop like this, current enters into the positive terminal, right? So I know Li is equals to flux, okay, N phi, right? This is the basic equation of inductor and this we'll learn in machines as well, but for now just understand this, Li equals to N phi. Now what else I can say? I can say that if I differentiate on both sides, right, this will be N d phi by dt is equals to L di by dt, where L is constant, right? So basically my voltage VL will be L dIL by dt. That is already written over here. Okay, that is already written over here. So if I differentiate on both sides, right? So now my voltage is related like this. So inductor, the property of inductor is it doesn't allow sudden change of current. So if I do the Laplace here, you will do the Laplace, like if you have studied already Laplace, you know, and in network theory also they have explained you Laplace. If you do the Laplace, right, Laplace, the equivalent Laplace circuit will be something like this. So if you do the Laplace inverse of this, VL of S will be SLIL minus LIL, 0 minus. So this will be the initial condition. So this voltage, right, whatever voltage it develops, it depends on the initial current across the inductor. And why does a voltage has to be developed? Because the inductor tries to keep its current same, and by trying so it has to develop some voltage so that that current is same. Okay, that is this amount of quantity of voltage, right? And this is SL, this is simply the inductive impedance provided in the frequency domain. So if I have a current like this, okay, if I have a current like this, let's say the current inside the inductor is something like this. So can I find out the voltage from this current waveform? Yes, right. What is voltage? Voltage is L dIL by dt. It is basically the slope of this, like proportional to the slope of this. So from this 0 to some value, right, from this to this limits, the slope is positive. If the slope is positive, this will be plus, right? This will be plus. Okay, and here from here to here, what is the slope? Value of slope is 0, right? Because slope is parallel to the x-axis, and whenever the slope is parallel to the x-axis, it will be 0. Okay, next this, right? Here slope is negative. You can see simple slope computation. If you have studied engineering mathematics, you will be able to simply find out the slope. This is 0. This is 0. Next, this is again negative. Okay, again negative. Now this is again 0, right? This is 0. And after this is positive, right? This is positive. So this will be something positive. Okay. Now, one thing we observe is that what is the instantaneous power? What is the instantaneous power? So instantaneous power is simply V into I. So in this region, right, in this region, my voltage and current both are positive. If both are positive, that means overall power in this region will be positive, right? And like my voltage is like this and current is entering, these two notation means the positive, right? If current is entering into the positive terminal, that means it is absorbing power. And here current is positive, that means current is entering, and voltage is also positive. So whatever polarity I assume, this will stay intact. Hence current is entering into the positive terminal. Hence I will say power is positive, right? Power is positive. That means it is absorbing power. So here this is acting like, in this region, right? In this region, this is acting like a load. Okay. Now in this region, what is the case? In this region, the power is 0 because voltage is 0, right? So it is not absorbing or delivering power. And what about this region? What about this region? So this region, right? Current is positive because this is above the x-axis, right? But voltage is negative. So here current is positive. So current is entering here, but voltage is negative. That means the terminals will be changed. So plus will be here, minus will be here. Hence current is entering into the negative terminal, or current is leaving the positive terminal. If current is leaving the positive terminal, that means it is delivering power. That means it is acting like a source in this region. Acting like a source in this region. Okay. And similar case here, again it is negative, voltage is negative, and current is also negative. So current is also negative, that is direction of current will also change, the direction of voltage will also change. Hence current is entering into the positive terminal. Again this will act as a load. Again this will act as a load. Okay, this will act as a load, right? Now this, what is this? So here this is 0 and this is 0, so overall this will be 0. Again this is positive and this is negative. So voltage is positive but current is negative. That means current is living like this and this is positive, right? Because voltage is positive. So I can say that current is leaving the positive terminal. Hence again this will act as a source. So like what I want to conclude here is that my inductor, right, can absorb and deliver power. Resistor can only absorb power, but inductor, although it is a passive element, but over a complete cycle the overall power will be 0. Okay, if you compute at steady state over a complete cycle, if it is a periodic waveform, right, the overall power across the inductor will be 0. Why? Because if you compute this, multiply and compute the area, right, it will be 0, because at steady state my inductor will be settling, and inductor is a passive component. It cannot net deliver power. But what can inductor do? It can absorb the power, whatever energy it has, it can store it for some time, then again it can deliver when it is required to deliver, right? That inductor can do. But overall net inductor cannot deliver power over the cycle. Over the cycle the power absorbed by the inductor will be 0 always. Okay, but it can deliver power, it can deliver energy by whatever it has stored for some amount of time. Okay, so that it can do. Okay, so that is the important thing about inductors. That is the important thing about inductors. I will tell in the points as well. Another thing to notice here is this right, this is a current control voltage source. Why is this a current control voltage source? Intuitively, if you want to understand, inductor doesn't allow sudden change of current. So it, like, current variable controls the inductor. That's why this is a current control. And why is there a voltage source? Voltage source, like, there is no intuition for voltage source, but voltage source is there to allow to not change the current. It doesn't allow the change of current. It doesn't allow the change of current, right? That's why voltage source is there. That's why this is current control voltage source. Okay, so there are a few points. Inductor resists sudden change in current. The direction of current cannot change suddenly unless an impulse voltage is applied, right? If an impulse voltage is applied, then obviously it can change its current. That we already know. We have studied in basic electric theory. Then inductor voltage can change suddenly. Polarity depends on the inductor current. So voltage can change suddenly, but current cannot. Okay, when inductor current is constant, voltage will be 0. When inductor current is constant, voltage will be 0. Okay, so like you can see, right, it is constant, voltage is not, current is not changing, so it has reached steady state. Hence the voltage has gone to 0. Now inductor voltage depends on the circuit context, but inductor current depends on the inductor as well. Unless a impulse voltage is applied, then the inductor current can change. Okay, now implications in power electronic converters. So what are the implications if we use inductors in power electronic converters? So inductors can produce high electromagnetic interference if they are present, right? Also results in heat loss over a short period of time, because I told you that if there is a constant current through the inductor, the flux will get saturated and there will be heat loss. That is a simple reason. Okay, now what is the voltage second criteria of inductor? That we already know, but still we need to revise this. This may be new to you as well. Okay, if the given circuit is stable and steady state is achieved, so we are achieving steady state and circuit is stable, then the average inductor voltage across the cycle will always be 0. What do I mean by this? So this is the inductor current, right, and this is the voltage. So if I just find out the average inductor voltage, so over a cycle. So this is repeating, right? This is a periodic waveform. This is repeating. So let's name this as T, and after every T cycles it is repeating. So let's name this area as A1, and let's name this area as A2. Let's name this area as A1, and let's name this area as A2. Okay, so what I can say is that if the circuit is stable and steady state is achieved, then I can say that this area A1 will be equals to A2. Why? Because the average voltage. How do I compute average? VL average will be what? VL average will be what? It will be integration like 1 by T, integration from 0 to T, V of T dt, right? V of T dt, and this will be equals to 0. Why this will be equals to 0? So if I want to dive deeper into it, right? So basically, what is my VL of T? VL of T is 1 by T dit dt, and this is again dt, right? From 0 to T. Okay, so this is my dt, right? 0 to T. So dt will get cancelled, and this will be remained with 1 by T integration of di 0 to T. And over a cycle, right, I have told you that inductor has reached steady state. What does steady state mean? Steady state means current will be constant. Current will be constant, or current won't change, right? Current won't change. That is what basically steady state means. Then only I can make the voltage 0. So here, if you're observing, I'm starting from this, let's say some I value. I'm starting from this I value. Then again, I'm coming back to this I value, right? Then again, I'm coming back to this I value. So the di is 0. As the di is 0, hence this will be equals to 0. So this is the voltage second criteria. Basically, inductor current should be periodic. Basically, these are the conditions for it to satisfy. Here, inductor current should be periodic. Charging and discharging both must occur in the same cycle. These are the conditions that needs to be satisfied, right? Inductor current must be bounded within finite values. So if inductor current is bounded within finite values and there is charging and discharging happening in the same cycle and it is periodic, and if the inductor voltage is also periodic, then obviously I can say that average voltage across the inductor will always be 0, because it will absorb some power and it will also deliver some power. It will absorb some energy and deliver some energy. Okay, with the help of inductive load in a half-wave rectifier, we'll understand this, what is happening. Okay, so this is about the inductor. Let's do a quick recap about the capacitors. Just hold on, I will check one thing quickly. Yeah, let's do a quick recap. So capacitor is basically related with charge and it is related with voltage. So if I differentiate this, this will be simply IC, dq dt is IC equals to C dVc by dt. So this is the voltage and current of capacitor, and this is the equation in time domain point of view. Then if I do the Laplace, right, if I do the Laplace and I draw the circuit, so this, like, I get a 1 by Cs, which is the impedance of the capacitor, and this is what? This is simply Vc0 minus by S. So this voltage source is dependent on the initial voltage. So this is a voltage controlled voltage source. So obviously there is no intuition why is this voltage source, that's fine, but this is a voltage control. So this time the voltage is controlling this, right, to make the change in voltage 0. Why? Because I want the voltage not change. So that's why this will try to not change the initial voltage. Okay, so that was basically it. Now let's plot this current waveform. Just hold on. Yeah, just plot this current waveform, right? So in terms of in case of inductors, we plotted the voltage. In case of capacitors, we will plot the current, because with the help of voltage, if you know the voltage, right, we can plot the current. Like basically it will be what? Again, the rate of change, it will be the slope of this voltage curve. So from this first cycle it is positive, from this next cycle it is 0. Okay, in this period it is 0, then again it is negative, then again it is 0, then again it is negative, then again it is 0, and then again it is positive. So again this in this region this is load, because both voltage and current are positive. In this region it acts as a source. In this region this is negative and this is positive. This again acts as a source, and in this region this again acts as a load. Both voltage and current are negative, hence overall power becomes positive only, it absorbs the power. Okay, so all these are there. Okay, like there is few points about capacitor as well. Capacitor resists sudden changes in voltage. The direction of voltage cannot change suddenly for capacitors, but if a impulse current is applied, then it can change. Okay, capacitor current can change suddenly, just like inductor voltage. Polarity depends on the capacitor voltage, like direction of current. Okay, now when capacitor voltage is constant, current will be zero. This I have explained graphically here. Capacitor current depends on the circuit context, because voltage will be controlled by the capacitor, but the current will be controlled by the circuit elements. Okay, and again the same implications, whatever implications I had in the inductor, the same implications will be here as well. Okay, so capacitors can also get heated and they can also provide EMI, right, high electromagnetic interference, and one example of EMI I have already explained in the first chapter. Okay, now what is the current second criteria? It is just similar as voltage second criteria here, right? The difference will be the average value of current over a cycle will be 0. So IC average, right, over a cycle will be 0. For that to happen, the following conditions need to be satisfied. That is, the circuit needs to be stable, steady state has to be achieved, then average capacitor current in a cycle will be 0. Capacitor voltage should be periodic, it should charge discharge within the same cycle itself, and it should obviously repeat. Capacitor voltage must be bounded within finite values. Capacitor voltage must be bounded within finite values. So yeah, that is the case. And like areas are this: A1 and A2. And if the average current is 0, that means basically whatever area I have contributed here, positive and negative area, both will be 0, both will be equal, and then only this average current will be 0. Hence IC average is 0, that is A1 equals to A2. Okay, A1 is equals to A2. So another thing I forgot to mention here, that your average power consumed by the inductor will be 0, right? PL average will be 0, because if you just compute this, right, if you compute the area, this will also be 0. Okay, compute the average power, this will also be 0, because inductor cannot consume any power in a cycle. Okay, it can store the energy and it can provide the energy whatever it has stored, but it does not consume it by itself, but a resistor in series with it will consume that extra energy. Okay, that you need to keep in mind. Inductor in itself doesn't consume any energy. Okay, and same case for capacitor as well. Capacitor in itself doesn't consume any energy, but it can store the energy, then again provide the energy back to the source. Okay, unless a parallel resistance is connected. Now what are these conditions used for in filters? So if you observe here, this is a simple LC filter, and if I see here, okay, that this is a low pass filter. Now Vi is equals to what? I am writing the simple this KVL, right? Simple KVL. So not Vi, sorry, this is Vs, right? Vs is equals to VL plus Vc. Okay, now if I take the average on both sides over the cycle, and I am assuming that this circuit has reached steady state. So if this circuit has reached steady state, this will be Vs average equals to VL average plus Vc, or you can write it as VO as well. You can write it as VO as well, because Vc is equals to VO itself, right? VO. Okay, so now what I can say? I can say that what is happening is that this VL average over a whole cycle will be 0. Now here, right, this is input, this is the input of what? This is the basically this is not the Vs actually, this is I should say this specifically, this is some value Vx, okay, else you will get confused with the supply itself. This is the output of half wave rectifier, right? This is the output, or I can say this is the output of rectifier that is being fed into a filter. Okay, that is being fed into a filter. So Basically here the thing is that I told you, right, we get ripples, and to fix those ripples we use this filters. And this what will happen is, if my, like this time, right, this is my Vx, right, this is my Vx. So my overall VL average will be 0 within a cycle. So VO will be simply Vx average, that is the average voltage of the rectifier. And what will happen is, the average value will be intact and the ripples will be reduced. The high amount of ripples were present, right? I can see, like this was the ripples, right? Huge amount of ripples. I want constant voltage. So what will this inductance do is that, not this inductance, sorry, this capacitance will do is that this will reduce the ripples of voltage. Okay, it does that. Okay, so next about the current. So my IO is equals to, not IO, sorry, my IX. This should be IX, not IL. This should be IX. Right, this is IX. My IX equals to IC plus IO. Okay, IC plus IO. So now what I can write? I can write this. I can take the average. So IX average will be equals to IC average over a cycle is 0. That means it will be equals to IO average. So the average current is intact, but due to this inductance, right, this will reduce the ripples in the current. Okay, this will reduce the ripples in the current. Okay, so even though the average current will be same only, it won't change the value of the current, but the ripples will get reduced. Okay, so you can study more about filters in analog electronics and in other playlists. Okay, but this much amount of theory is required for filters only, for understanding this. Okay, and this current second criteria and voltage second criteria will be used in choppers as well. So if you aren't able to understand this, please go through it once again, because this will be used in choppers as well. Okay, now let's go to the first analysis, that is the pure inductive load. So how do I analyze this? So first of all, I am analyzing this with a diode, then I will analyze this with a SCR. So in this case, right, we have to understand what is happening just after omega t equals to 0 plus. So first I will assume this as a diode as off. If the diode is off, so the inductor previously has no charge. So if the inductor has, sorry, not charge, inductor previously has no flux. So if the inductor has no flux, hence the IL 0 minus will be 0 amperes. IL 0 minus will be 0 amperes. Next, if the IL 0 minus is 0 amperes, there is no change in the current as well, right? Because initially the current was staying at 0 only. So VL 0 minus will also be 0 volts. Okay, because DIL by dt is 0, because there is no change in the current, because current is constant, that is 0 amperes. So next, what is VD? So just at omega t equals to 0 plus, my VD will be something. VD will be equals to what? VD will be equals to VS, because this is 0 potential, this is Vs, so the VD will be equals to Vs, and this will be something positive. As soon as this becomes positive, the diode will turn on. Diode will be on. Now as the diode turns off, what will happen? As the diode turns off, a supply of Vs will be directly connected across the output. So VO will be equals to Vs, and your VD will be equals to simply 0. So what I can say that what will be my IS or ID current, it will be equals to IO, and what is it? It is simply equals to integration of 1 by L 0 to T voltage across the inductor, right? Why is that the case? Why is this the case? Because here, right, here if you observe one thing carefully, that after just this switch closes, my VL becomes VS, that is this supply, and what else is happening? I know that my VL is equals to L di by dt. If I integrate on both sides and divide by L, my IL will be this value only. Okay, this value will be IL. So I will replace this VL with VS. So this will be 1 by L. This will be 0 to T Vm sine omega t dt. So in this case, right, I am not integrating with respect to omega t, I am integrating with respect to dt, because the formula, inductor voltage formula, has dt in it, not d omega t. That's why. That is the basic reason. In previous cases, integrating with respect to d omega t or dt wouldn't have made a difference. That's why we integrated with respect to d omega t. But here it will make. That's why I am integrating with respect to dt only. So this will be 1 by L into Vm into, like, this will be 1 by omega divided by 1 by omega, and this will be, basically this value will be 1 minus cos of omega t. 1 minus cos of omega t. So this will be basically, if I just rewrite this in a better manner, this will be Vm upon Vm upon omega L. So this is the value of the current. Now this is the current, this is the diode current. So when will the inductor turn off next time? So sorry, not inductor, when will the diode turn off? So when does diode turn off? So diode is off when basically either my ID current is 0 or the voltage appeared across the diode is negative. Then only diode will turn off. So obviously I can have a control over this current because I know the expression of this current, and the voltage across the diode depends on the current because the voltage across the inductor depends on the current. So I will solve everything with respect to current. So when is the current going to 0 next time? When is the current going to 0 next time? So I have to equate this with 0, right? This one with 0. So 1 minus cos omega t should be equals to 0. So if I equate this with 0, so my cos omega t should be equals to 1. So basically it is getting to 0 after every 0, 2 pi, 4 pi, all this time, right? So it is turning off just at 0, 2 pi, 4 pi. So basically when it is turning off, right, then again it is turning on. Why? Because I have analyzed this just at t equals to 0, omega t equals to 0 itself, right? And at omega t equals to 0, it turns on as well, right? So when it is just turning off, it is turning on again. Why? Because the current again goes to increases somewhat due to this cos function. You just put the values, right? 0 plus 2 pi plus something like this. This will be something greater than 0. So the graph across the inductor current will be look something like this. It will be 0 for a very small amount of time. So I told you, right, the definitions of continuous, discontinuous, and like at the starting of the lecture I told you just continuous. So this is on the edge of the continuity. Edge of the continuity. This is at the edge of the continuity, right? So because this is just getting 0 for an instant, that's why this is known as continuous, but this is just at the verge of discontinuity. Edge of continuity and discontinuity. So current will be something like this. You just plot this graph, right? This current expression you plot, and you will get out your current something like this, and your voltage across the diode will always be 0. Because diode is always almost on, because here as well, after just this is, let's name this as 2 pi. After just 2 pi, this will again turn on. After just 4 pi, this will again turn on. Okay, so this will always be on. This will be the analysis. This is the boundary of edge / boundary of continuity and discontinuity. So in the lecture 1 as well, I should rename this as boundary because that is also important. So I'll just quickly rename it. Okay, let's proceed with the analysis. So obviously this is a 2-quadrant converter. Why is it a 2-quadrant converter? Because if you observe here carefully, right, in this region, my Vs is equals to VO always, right? Because this diode is never turning off. So Vs will always be equals to VO. So this will follow just the input supply, and the current is always positive. So in this 0 to pi, voltage is positive, current is positive. Hence, my power will also be positive. That means it is absorbing power, because power is positive. That means whatever notation I have followed, current is incoming into the terminal of the positive terminal of the voltage. So I will absorb some power. Then in this region, right, in this region I am absorbing. In this region I am actually delivering power. Why? Because voltage is negative but current is positive. So current is flowing like this. The voltage polarity has flipped now. So current is exiting from the positive terminal. So I will deliver power here. Over a whole cycle, I will neither absorb nor deliver. The overall power over a cycle, okay, power of like average power over a cycle will be 0. You compute the area of this, you find out, you write I of t expression, I of t is this, right? I of t is this. You write V of t expression, V of t is simple Vm sin omega t, Vm sin omega t. You integrate the multiplication of those two within a cycle, and you will see that average area is 0. That is, average power will be 0. As explained earlier as well, that inductor doesn't absorb power over a cycle, okay? So that is the case, but this is a 2-quadrant converter. Because why? Because the inductor can deliver as well as receive power, and inductor has the capacity to keep the diode on even though the supply voltage was negative. Still the diode was on. How was the diode on? The inductor itself developed a voltage. That kept the diode on, that kept the anode to cathode voltage positive. That's why current was still flowing and diode was on. So the inductor itself developed a voltage, okay? So that is the important part over here. So that's why the diode was on, okay? So that was the explanation over here. Now let's basically move on to further analysis of SCRs. So SCRs will just be the same. There will be one slight difference. What will the slight difference? I will explain. So here it is controlled. So first of all, for SCR, right, we have to find out the forward blocking mode, the period of forward blocking mode. So again the same thing. Initially at omega t equals to 0 plus, if I just draw a sinusoid waveform, okay, if I just draw a sinusoid waveform at omega t equals to 0 plus, right, what is the voltage Vt? Vt voltage will be like, it will just follow the input, right? Why? Because this end potential is 0 for the same obvious reason, because IL of 0 minus is 0 and VL of 0 minus will also be 0 because it is not changing. So VL of 0 minus will also be 0 volts, okay? VL of 0 minus will also be 0 volts. Next what is happening? Next basically, just hold on, draw this in a better manner. Okay, so now this is 2 pi, this is pi. Now as soon as this SCR is triggered, right, as soon as this SCR is triggered, it will try to flow some current. Yeah, sorry for the interruption. So here, right, this voltage will be sinusoid, and at, let's say, like, what is the forward conduction or forward blocking period? Forward blocking period is from 0 to pi, right? 0 to pi, because that is the time period for which the SCR voltage is positive, okay? So yeah, it is in the forward blocking region here, and it is in the reverse blocking region in this region, right? So obviously I can turn on my SCR here only, so the range of alpha will be from 0 to pi. Now here, right, this can change, this can change. How will this change? I will say when we have different circuits, okay? So let's start the analysis from 0 to alpha. 0 to alpha, this same analysis will follow. Basically the SCR will be off, hence the current will be 0, hence basically my VO will also be 0, which is equals to VL, which is not, current is not changing, hence voltage will be 0, which is 0, right? And obviously IO is 0 amperes. Simple analysis. Now as soon as my, and what I can say is my VT is greater than 0, VT is greater than 0, hence this will be in forward blocking mode. VT will be in forward blocking mode, okay? So now as soon as I trigger the SCR at omega t equals to alpha, as soon as I trigger the SCR will be turned off. Now I don't know until when this will conduct, because the conduction depends on the inductor. Okay, why? I will explain just in a second. Okay, so at omega t equals to alpha, SCR is triggered, hence SCR is on. So if SCR is on, Okay, so if SCR is on, what will happen? VT will be 0. Now as VT is 0 volts, so my output voltage VO will be equal to simply VS. So my VL also equals to VS, right? So the important point is VL will actually change now. VL will not depend on the supply, VL will depend on the source. Why? I will explain. What is my IS? IS equals to IT equals to the inductor current. Okay, just hold on, I will just check one thing. Yeah, everything is fine. Equals to the inductor current equals to, again the same form, right? Integration of this from this time it will not start from 0, it will start from alpha, because at alpha the SCR starts to conduct. Before that the current was 0. It is simply, now what is VL? VL is simply VO, right? So this will be VS, that is Vm sine omega t, d omega t. Now what will happen here is, what will be this IS value or IO value? This IO value will be equals to this same thing will be present, Vm by omega L into cos of alpha minus cos of omega t. Okay, so what I can say, what can I say? I can say that at alpha equals to at omega t equals to alpha, the current should be 0, right? Because just before alpha, what was happening? The SCR was off and there was no current flow. So inductor will try to keep the same current just after alpha as the SCR is turned on. So if I put here omega t equals to alpha, this is satisfying. This becomes 0. As this becomes 0, the current becomes 0. So the current becomes 0. Now the important point here is that the current becomes 0. What is the voltage? So what is happening here is that the inductor in itself actually produces a voltage so as to make this current 0 at that particular time. Okay, that is what that inductor produces. So yeah, I hope you got the point. Now when does this SCR turn off? So when will the SCR turn off? Either when the SCR comes into the reverse blocking mode, or when the current through the SCR is 0, or it is below the holding current. So holding current in this case ideal SCR is 0. Okay, so when this goes to 0, if I plot simply cos omega t, right? If I plot cos omega t, this will be this, and I am doing cos alpha minus cos omega t. So when is this crossing this particular value again? So in a sine wave or a cos wave, it crosses a particular value twice within a cycle. Okay, at cos omega t equals to alpha, this will be equals to cos alpha. At omega t equals to, what is this value? This is equals to pi minus alpha, right? Omega t equals to pi minus alpha. So at omega t equals to pi minus alpha, again this value will be equals to cos alpha. Okay, this value will be equals to cos alpha. So at this moment of time, this overall thing goes to 0. This current goes to 0. So at omega t equals to pi minus alpha, IO goes to 0 ampere. Goes to 0 ampere. Okay, so it will only conduct from alpha to 2 pi minus alpha. Okay, so not pi minus alpha, it will be 2 pi minus alpha. Okay, so it will only conduct from alpha to 2 pi minus alpha. Okay, this is not pi minus alpha, sorry for that. This is 2 pi, right? Because this overall cycle is 2 pi. So what will happen after 2 pi minus alpha? 2 pi minus alpha, this SCR will be turned off, and as the SCR is turned off, and as the current also becomes 0, so what will happen? After that, current won't change. So my basically my IL is 0. IL, or I can write my IO as 0 ampere, or IT as 0 ampere. Also my VO will be equals to VL will be equals to 0, because the current won't change anymore. Current will remain at 0 only. So this will be 0. Okay. So yeah, this is VO is this. So now, right, what can I say? What can I say is that SCR goes into reverse blocking mode. Why? Because my VT will be this time equals to VS, because VO is 0. So VT will be equals to VS, and VS is this time, right? VS is negative. VS is negative. Hence VT will be negative, and SCR will go into reverse blocking mode. SCR will go into reverse blocking mode. Okay. So basically natural commutation will happen. Why am I putting more emphasis in this analysis? Because later on we'll study about RLE load, and if you don't understand these basic things, right, about inductor, you will not be able to solve RLE loads. Okay, because RLE loads are the most important ones. Okay, so this will be the waveforms. Basically this will be the waveforms for my output voltage and my this inductor, sorry, not inductor, this thyristor voltage, right, this SCR voltage. Now important point is, as soon as like this inductor develops this particular voltage and it tries to keep its current 0. Okay, it tries to keep it current 0 because this is the current plot, right? This is the current plot. One more important point to here note is that, like, this plot is for pure L and the voltage waveform is something like this. So again, the average voltage, output voltage is 0, and average inductor voltage should also be 0. That is true in this case. If you find out the average, it will be 0. The thyristor voltage is like this. It is only blocking in this region, and it is in the forward blocking mode in this region. Okay, after that it is never blocking. It is always on. It is kept on even after this, when the input goes to 0, due to the inductor, as inductor tries to like keep the same amount of voltage so that the current keeps on flowing. Okay, that is the duty of inductor here. So this is the natural commutation time. Okay, and what about the current? So here, right, the current will be something like this. Current will be something like this, that it will be like this time will be same only for this will take same time, that is from 2 pi minus alpha to pi minus alpha. This will be symmetric because it is conducting, like it is in this region, right, in this region. So in this region, if I say in this particular region where the current is 0, the instantaneous power is 0. Instantaneous, if I just take some other color, power is 0, right? In this region, what is happening? The power is positive because voltage and current both are positive. So power is positive, that is basically it is absorbing. In this region, what is happening? In this particular region, in this region, power is negative, that is it is delivering power, right? And in this region again, power is 0. Power is 0. So it only the duration for which it absorbs power, it delivers the power. So next, like if you compute the power over a whole cycle, it will be 0 only. If you compute the power, inductor neither will absorb a power or deliver the power. So basically these are a few key points about inductive loads. When an inductive load is present, the device may not get turned off even though the voltage, or the I can say the supply voltage, even though the supply voltage has become negative due to the stored energy in the inductor. So the stored energy in the inductor keeps the SCR on and keeps the current flow on. So it helps in continuity of the current. So current still flows. So that's why inductor is used in circuits to help in continuity of the current. This is because the energy previously stored in the inductor is still present and it tries to deliver it to the load by making the current continuous. Okay, so I hope you got the crux of inductor. So here there are a few parameters about inductors in case of SCR. So what is the conduction period? Over a 2 pi cycle, it doesn't conduct for only this alpha and this alpha angle. So over a 2 pi cycle, if I subtract 2 alpha, this will be my conduction period. And what will be the natural commutation time? Natural commutation time will be alpha by omega. Why? Because it is in the reverse blocking mode for this region and it is in the forward blocking mode for this region. So natural commutation time is the time for which it is in the reverse blocking mode. So it will be alpha by omega. And this is the basically the coordinate diagram. So it receives, absorbs energy and also it delivers the energy. Now, what is the peak inverse voltage? Peak inverse voltage. Peak inverse voltage is the maximum voltage that may appear across a diode, across a device. So in this case, right, I haven't mentioned about the peak inverse voltage previously in previous parameters as well. I will keep those. In this case, what is the peak inverse voltage? The maximum voltage that appears across a diode, right, is what? Vm sin alpha only. Vm sin alpha. Okay, it is not any other value because this is the value from which the SCR is in reverse mode. Okay, so it will be Vm sin alpha only. And okay, just hold on. If the alpha is greater than pi by 2, if the alpha is, let's say, greater than pi by 2, so it has to block this pi by 2 angle as well. It has to block this reverse pi by 2. Okay, this value, right, this value is for when my alpha is between pi by 2 to 0, and it will be equals to Vm when my value is between alpha is between pi by 2 to pi. Why is that the case? Because like if my alpha is between 0 to pi by 2, right? So after that what will happen? The inductor will keep the SCR on, so it won't have to block any voltage, and it will keep it on until 2 pi minus alpha. So if it is between 0 to pi by 2, so Vm will, the SCR will never see Vm. So if I trigger the SCR somewhere here, right? If I trigger the SCR somewhere here, okay, the SCR has to block this forward voltage, and SCR will also have to block this. It will only conduct until this, and SCR will also have to block this reverse voltage of Vm. So obviously peak inverse voltage will change, then it will not be equals to Vm sin alpha, it will be simply equals to Vm, right? So like peak inverse voltage, I've explained in my prerequisites what does peak inverse voltage mean. And there are few terms, new terminologies here. One is the extinction angle. What is the extinction angle? The angle at which the current becomes 0. So represented by angle beta, introduced in AC to DC converters with inductive loads. So this is specifically used for inductive loads mainly. Determines the point at which the inductors gets fully discharged. Basically the current IO becomes 0 amperes. Current IO becomes 0 amperes. Generally the case is like beta is equals to, in this case beta equals 2 pi minus alpha. 2 pi minus alpha, the current becomes 0. And generally what will happen is, in most cases beta will be greater than 2 pi minus alpha, then only the motoring action will happen, else motoring action won't happen. But not 2 pi, sorry, generally beta is greater than pi, but this can be, this can change as well. This can change as well. Okay, this is not always the case, this can change as well, but generally beta is greater than pi, but beta can be less than pi as well. Now what is another terminology? Another terminology is conduction angle. So conduction angle is represented by gamma and determines the duration for which the device conducts. Basically it is a gamma only. Okay, and in this case what is the duration of T on? Duration of T on, right, I've already computed, 2 pi minus 2 alpha. So it will be simply, here in this case it will be beta minus alpha. Okay, beta minus alpha, or if you put beta equals to 2 pi minus alpha, you will get it as 2 pi minus 2 alpha. Oh, these are just the terminologies that you should know. Okay, so what are the advantages of inductive load? Continuity of load current increases, as I told you, right? Even though the supply voltage is negative, still current is flowing in the circuit. That means the continuity has increased. Ripples of the load current decreases. Like it reduces the ripple of the load current because inductor controls the change in current. It doesn't want any change in current. So if there is a huge change in current, if I pass it to inductor will like make it voltage, its own voltage, change its voltage such that the change in current reduces. So that's why inductor is helpful. Power factor improves, okay, in the input side, and operates in two quadrants. So these are advantages. We can operate in like deliver or in absorb mode as well. What is the disadvantage? The average output voltage reduces. Why? Because average voltage across inductor will always be 0, and you can observe right here. What is the average output voltage? Even though the current is average current has increased, but the average output voltage is simply the average of the supply, or simply like this, right? It is simply like this, and it will always be 0. So once we will have R load, there we will also see the average voltage has increased, because it even though the voltage is negative, it is coming across the output as well. So negative voltage is also coming across the output. Due to that, the average voltage, output voltage is reducing. So average power can also reduce. Due to this, power reduces, and as the power reduces, the efficiency will reduce, as said in this second point. So this is a question. Let's solve this question basically. So this there are two questions that we'll solve, and then we'll end the this lecture. So we have to determine the following for the given circuit: maximum current through the diode in the first cycle and steady state. So what is the maximum current that can flow through the diode in the first cycle? So maximum current that can flow through the diode in the first cycle is what? So I am triggering it. I'm like, this is just like a trigger, right? But I'm just turning it on at t equals 2.5 milliseconds. After that, I'm not turning it on again. Okay, this is just a switch. I'm just turning it on at t equals 2.5 milliseconds. So what will happen is that if I have this supply, and what is t equal to 2.5 milliseconds? In the previous lecture I told you a shortcut, right? If I have a 50 hertz, so this is a 50 hertz, right? 314 t means 50 hertz supply. If I have a 50 hertz supply, then 10 milliseconds means pi by 2, sorry, not pi by 2, 10 milliseconds means pi, and pi by 2 means 5 milliseconds, and pi by 4 will mean 2.5 milliseconds. So I am turning my this switch on somewhere here, and the voltage is positive, and initial voltage across the inductor was 0 because there is no change in current. So the diode sees a positive voltage, so diode will instantly turn on, and my VO will be equals to VI simply. In this region, VO will be simply equals to VI, right? Diode will turn on, and then again, what will happen? It will turn off when? It will turn off at this particular pi minus alpha, right? This is pi by 4. So it will turn off as not pi minus alpha, that it will turn off at 2 pi minus alpha, that is this value. Okay. So it will turn off here. So what is this value? This value is 2 pi minus alpha, that is 2 pi minus alpha. 2 pi minus pi by 4, that is, if I multiply 2 pi, 8 pi minus, this is 7 pi by 4, right? So at this particular angle, it will turn off. Now after that, what will happen? After that, the inductor voltage is 0, 0, 0. Then again, the inductor voltage is 0 and supply becomes somewhat positive. In this region, right, the diode voltage is negative, hence it will be reverse bias. Now at this point, the inductor voltage is not the inductor voltage. The diode sees some positive voltage and the inductor voltage is 0. So diode will see some positive voltage and it will become forward bias. Hence the diode will get turned on and inductor will flow some current, and this will become just like a simple diode circuit, right? Simple diode circuit with pure resistance, and this will always conduct after this. So for the first cycle only, the current will be 0 and it will increase. The peak will always occur at pi, and then again this will stop conducting at 7 pi by 4, and this is pi by 4, and this will not conduct here. Okay, this will not conduct until here, but after this will be just like a simple diode circuit, the first converter that we analyze with diode and inductor, right? So this will be simple diode circuit. So that is the case. So here what are they asking? They are asking the maximum current to the diode in first cycle and steady state. In the first cycle, the maximum current will be somewhat lower than this. So what will be the maximum current here in the first cycle? It will simply equals to what? So here, right, I have already derived this, right? So if you want to compute the maximum current, right? Maximum current here when it is triggered in alpha. Where did it go? Okay, I haven't derived the maximum value. So maximum value will be what? Basically the maximum value will be occurring at, okay, where is the expression of current? Here, right? So IO peak will always occur at omega t equals to pi. And why will it occur at omega t equals to pi? Because if you observe, right, here it is absorbing the power. So in this region it is absorbing the power. Then just after this, the supply voltage becomes negative and the output voltage also becomes negative. It is delivering. So as I am delivering the power, obviously how will I deliver? Inductor stores its energy in terms of flux. Flux is proportional to the current, so it will lower its current, right? So energy through the inductor will reduce, that is EL will reduce. And EL is equals to what? Half Li square. So L is constant, half is constant, so I has to reduce, right? Because energy stored across the inductor will reduce, so I has to reduce. So I will reduce here, so it will be peak, it will hit peak somewhere around here, and then only I will reduce. So that's why peak will happen at omega t equals to pi. So at omega t equals to pi, what is the value? It is Vm upon omega L, and this becomes what? Minus 1, and minus of minus 1 is plus 1, and this is cos alpha. So this becomes 1 plus cos alpha. Okay, so this becomes 1 plus cos alpha. So Vm upon omega L into 1 plus cos alpha. So yeah, this will be the case. So in this case, what will be the peak value? The peak value in this cycle will be IO peak in first cycle will be equals to Vm upon omega L 1 plus cos alpha. Alpha, like alpha in our case, hypothetically hypothetical alpha is pi by 4, right? Because hypothetically I'm closing the switch at 2.5 milliseconds, which is angle equivalent of pi by 4. So Vm will be what? Vm will be this 100 upon omega L. Omega is 314, L is 10 millihenry, so this will be 10 raised to power minus 2 into 1 plus under root 2. Okay, so this will be equals to what? If I just compute this value, right? Just real quick, I'll just compute this value. Just hold on a second. This will be 100 upon 314 into 1 plus 0.7. Okay, sorry, everything got messed up. So 1 divided by root 2 plus 1 into 100 into 100 divided by 314. So this will almost equals to 54.36. Okay, this is for the first cycle. Okay, they have asked us for the first cycle and for the steady state. And steady state, what will this peak value? This peak value will be larger because this is energizing for a larger amount of time. This is energizing for pi. Okay, and in this region it is energizing for pi minus alpha. That's why the peak current was lower and the peak current will be higher. Okay, so IO peak as steady state equals to what? It will be equals to Vm upon omega L sorry, it will be 2 Vm upon omega L, right? 2 Vm upon omega L. In this case also I have forgotten to compute the peak value. Okay, in the diode case as well may have. So I have forgotten to derive the peak value. Peak value will happen at pi, and at pi, right? At pi. So my IO peak, diode will be off here, but what will be my IO peak? IO peak will be again at omega t equals to pi, because after that the SCR, so not the SCR, so the inductor is releasing its energy. Okay, it is de-energizing. So if I put the expression here, omega t equals to pi, this will be minus 1. Minus of minus 1 is 1. So this will become 2 Vm upon omega L at omega t equals to pi. Okay, so this will be 2 Vm upon omega L. So if I just write this, right, if I just write this here, 2 Vm upon omega L, so this will be equals to 2 into 100. So Vm is 100, right? 100 upon omega. Omega is 314 into 10 raised to power minus 2. So this will be, I'll just compute it, 200 into 100 divided by 314. So this will be 63.695 amperes. So this will be the peak value of inductor current. Okay, so in the part B, what are they asking? In the part B, what are they asking? They are asking us about the power factor of the source and load. What is the power factor of the source? So what is the power factor of the load? So is the like, if I tell you, just see this as block diagram. What is the power factor? This is simply a purely inductive circuit. No resistance is there. So obviously power factor will be 0. And if you want to understand intuitively as well, power factor is what? Cos phi L is what? It is simply PO upon SO, right? And I know the average power across the inductor will be 0. If you just compute the average power throughout the whole circuit, you integrate the product of voltage and current, you will see it will come out to be 0 by S0. So power factor will be 0. Like that also you can understand intuitively. Also you can understand that inductance, pure inductance doesn't have any AC component, so that will also be 0, right? So that is the case. Next, source power factor. So whatever the load power load power is, it will be equals to my source, right? PO, it will be PS upon SS, which will be equals to PO upon SS. Why is that the case? Because I have assumed that I have a ideal converter. Okay, converter is not converter is not absorbing any power, so that's why this source power factor will also be 0. Now power reduces, hence efficiency reduces, as I explained in the disadvantages fact, right? So this is the B part. And efficiency is also 0, right? Because the power is 0, hence efficiency will also be 0, because efficiency what PDC upon P normal PO, as this power is also 0, DC's power is also 0, so both of these will be 0. I cannot conclusively say, because it will be 0 upon 0, so we shouldn't have this in the question. Because efficiency I cannot say, because it is coming out to be 0 upon 0 format. But average voltage definitely I can compute. This average voltage will be what? It will be, okay, it will be simply equals to 0, right? Average voltage will be simply equals to 0, because if you just take the average inductor voltage, I know over a cycle, if it reaches steady state, will always be equals to 0. If you compute the average, this will be 0. So part C is average voltage. Okay, so VO average will be 0. So these are the answers. Now let's come to the next question. So next question is pretty similar only. We have to determine the following for the below circuit, that is conduction period of the SCR. Forward period SCR is conducting and extinction angle. So this is the pure inductive load, and I have explained the working of SCR. So I will write this directly here. What will be the conduction period? Like all the working I have explained, you just repeat that over and again for understanding this question. Conduction period will be simply, like at alpha it will be triggered, so current will increase from 60 degrees, then it will reach maximum at omega t equals to pi, then it will reduce to 0 at when omega t equals to pi minus what, or 180 360 minus 60, that is 300 degrees. So it will conduct from 60 degrees to 300 degrees. So what is the on time? So if I write this in terms of radians, right? So this will be equals to what? This will be pi by 3 to what is this? Pi is 180, right? Difficult to compute. 2 pi is 360. 2 pi minus pi by 3. 2 pi minus pi by 3 is, that is 6 minus 5 pi by 6. 5 pi by 6, right? So this will be 5 pi by 6. Yeah, I had made a mistake over here. This should be 5 pi by 3, right? So if I want to compute, like two things can be computed here. Either the conduction period in angles. So what will be the conduction period in angles? It will be 5 by 3 minus pi by 3, which is 4 pi by 3. This can be the answer. Or T on, right? T on. Okay, the conduction period can be T on. Okay, so this will be equals to simply the time for which it is on, which is 4 pi by 3 the conduction angle divided by the omega. Okay, omega is 314 in our case. So if you just compute this will be almost around, if I just compute this 4 into, or I can write this as this, right? I can write it like this. So this is what 2 pi f, right? It is 50 Hz, so this will be 2 pi into 50. So this will get cancelled. This will be 2 and this will get 25. So this will be 1 by 75. Okay, this will be 1 by 75, and you can compute in calculator whatever this will be. Now what is the second? Second is the extinction angle, that is beta. And in our case, what is the extinction angle? It extinguishes just after here, right? Just here, right? 2 pi minus alpha, that is pi by 3. So 2 pi minus alpha, that is pi by 3. So it is equals to simply 300 degrees or 5 pi by 6, whichever units they are asking the answer. So these two are the answer. These two are the simplest one. Like this is A, this is B, A, B. Okay. So like this you can solve the questions. So this is basically end of pure inductive load, and in the next lecture will be the most important lecture. We'll study about RLE loads, and we'll do more questions on that. Okay. And after that we'll learn about freewheeling diodes, and that will be the end of the half wave rectifier, and then we'll start with the full wave rectifier. So thank you for watching, and I will see you in the next lecture.